Hello guys, welcome back. And it's really a midnight over here. I'm in Kolkata, so I don't want to really disturb you, so my voice is maybe a bit low. So why I did this video because today's problem of 2021, like 30th August ka problem is actually I couldn't do one part in the first part. I mean, I couldn't do this y mod alpha is less than equal to 1, that part. So please go to our webpage and you can check the first part ka solution, that why it's a cumulative distribution function. So this is for the second part, which you couldn't do in the first part because I did some calculation mistakes. I didn't want to waste your time. So now I have got back with the solution with of the y mod alpha is less than equal to 0. I hope all of you can hear me clearly. Just give me a minute. Let me just verify. Perfect. Yeah. So since all of you can hear me clearly, let's really go back quickly to the let's scroll through the whole idea of the part one. So how do you get the part one solution? You can go to the link. There is a link of the problem, solve a problem a day. That link, go to there. The first part ka link is linked into that problem list, and then you can actually go back and you can also see the first part and then come back and see the second part. Okay. So it's for the second part discussion, why mod alpha is less than equal to 1. So that one and this one, and let's discuss that. So in the first part we have discussed the properties of like the CDF and why it's actually a CDF, but I got stuck in the middle where I sort of wanted to show that it's actually I showed, in fact, alpha is less than equal to like alpha is greater than equal to -1. That part I showed, but I couldn't show that mod alpha is less than equal to 1. Like alpha is less than equal to 1 is valid solution. And in fact, I got a really weird bound that alpha may not be actually 1. Upper bound of alpha is not 1, but alpha bound of alpha is rather this weird quantity, okay, which is much more like the low yeah, upper bound of alpha can is actually this quantity, okay, which is much more than 1. That's why I was facing a bit of issue to actually show that live. I did some calculation mistakes, but today now I will show why alpha is less than equal to 1. So let's scroll through the whole thing. The h of x comma y is this, and let's take the uniform random variable. X follows uniform, then f of x is equal to x, the CDF, and g of y is equal to y, where x and y are this. And you will see how beautifully it transforms into the result. And we have the new distribution function based on this two uniform distribution, that xy into 1 plus alpha into 1 minus x into 1 minus y, which we distributed to get this one. Okay. So now what I will do is the following, that I will actually like write the bound of on, or like write the bound that we have for f of x comma y. So f of x comma y has two bounds. That this is something really interesting. The h of x comma y has two bounds, that is equal to greater than equal to 0. So since x and y are non-negative, in fact, if it's 0, then it's something not interesting. If x and y are greater than 0 and less than 1, in that case we are considering. Otherwise it's equal to 0 always. You can actually verify that. So therefore we can actually take this xy to the bottom and it will get vanished, and we get that alpha is greater than equal to -1. 1 gets this side, and 1 by 1 minus x and 1 minus y gets below. So therefore alpha is greater than equal to minus this comes. And similarly, if you do less than equal to 1, you get alpha less than equal to this weird quantity. So let's not think about what is this, but let's understand that alpha is actually, okay, let's think about this. Okay, let's think about this, actually very important. um, so understand, alpha is actually less than equal to all the like values. Let's like not discuss this one, because we have already shown that alpha is greater than equal to -1. That comes from here. Let's discuss alpha less than equal to +1 part. So in that alpha less than equal to +1 part, what we have done is that we have actually shown that alpha must be less than equal to 1 minus xy into by xy into 1 minus x into 1 minus y. Now understand it very carefully, that x and y are less than equal to 1, and if alpha is less than equal to, for all of this, alpha is less than equal to this quantity for all values of x and y. Understand this very carefully. If you have a really big set, like very big set of numbers, and you know that a single number is actually less than equal to all the number in that set. Okay, here if you vary x and y, you get various numbers. Okay, so on the right hand side, so therefore alpha is less than equal to, therefore what, alpha is less than equal to minimum of all those numbers. Since alpha is less than equal to all those numbers, alpha must be less than equal to minimum of all those numbers. So therefore you have to find out the infimum of the alpha is less than equal to the infimum of all those numbers. That's the best bound we can have. Let's see how we can apply this to the other part. Let's me discuss that also. So from here we have gone that alpha is less than equal to, greater than equal to minus 1 by 1 minus x into 1 minus y. Since alpha is greater than equal to every such possible x and y value, that means what? All these numbers ka supremum, okay, all these numbers ka supremum, alpha is greater than equal to that. So alpha is greater than equal to set of all numbers. That means alpha is greater than equal to supremum, the maximum of all those numbers, right? So using that, you can actually show that. I mean, let me just do that. So using that, actually, you can show like 1 minus, so 1 by 1 minus x into 1 minus y is less than equal to 1. So 1 minus x by 1 minus y is greater than equal to 1. And if you do minus of this, is less than equal to minus 1. So supremum of all these numbers of x and y is less than equal to 1 minus 1, because also you can check that for x is equal to 0, y is equal to 0, you will get this minus 1. So supremum is attained. So this is actually, supremum is less than equal to supremum is actually equal to minus 1. So it's actually equal to minus 1. So you get that alpha must be greater than equal to this minus 1. This is super important. This is super beautiful actually. Okay. Similarly, we're applying over here that alpha is less than equal to 1 minus xy by xy into 1 minus x into 1 minus y. So it turns out that alpha must be less than equal to infimum of all the numbers. So we'll try to find the infimum, and that for that we need multivariable calculus. Okay, and but let's not go into that. We want to show that in fact the infimum. So we want to show that alpha is less than equal to 1. We want to show that alpha less than equal to 1 is a valid bound. So that's why it can only be held if infimum is greater than equal to 1. So if we can show this, the following, that alpha less than equal to 1 less than equal to infimum of xy 1 minus xy by xy into 1 minus x into 1 minus y, then you can show that actually the alpha is less than equal to 1, and this happens. So this, if we show that, then we are done, right? We are done. Our aim is to show that alpha is less than equal to 1 is a valid solution. So therefore we get that 1 minus x. So to show this, you can also show that 1 minus x by x minus y for all xy values is greater than equal to 1. Then their minimum will also be greater than equal to 1, right? So their infimum will also be less than greater than equal to 1. That's what we need to show here, right? So if we can show this, then we will show this. So let's show this value, that y 1 minus alpha 1 minus xy by xy into 1 minus x and 1 minus y is, what is the relationship with 1? So let's multiply both sides, positive numbers on both sides. So multiply it, the sign will not change. So 1 minus xy, expanded it, so you get xy minus xy x square y minus xy square plus x square y square. So you take the negative terms on both sides to get positive terms. So you get 1 plus x square y plus xy square. Some relationship here, the relationship is less than equal to 1 or greater than equal to 1. Which relationship, I don't know, that we are yet discover now. Is greater than is something 2xy, this xy comes here, and this x square y square. So there's something really interesting. So how to find a lower bound? So we want to find a lower bound. We want to show this is greater than equal to 1, right? This is what we want to show. I don't know whether it's true or not. So find a lower bound to this. So we will apply something called AMGM inequality. So AMGM inequality link is given in the description below. Do check that AMGM inequality link. But let me set the result which we'll use here. The AMGM inequality tells that if A, B, C are non-negative integers, then A plus B plus C is greater than equal to 3 into cube root of A times B times C. This is super interesting. It's super beautiful actually, and you can check the link of the AMG inequality below, or you can search anywhere in the Google and you can learn about AMG inequality. And if you apply AMG inequality on the left hand side, you get 1 plus x square y plus xy square is greater than equal to 3 times, let me expand that, 3 times cube root of x square y, 1 times x square y and 1 and xy square. cube root of this. So it's like x is cube, y cube. So you get 3xy, right? You get 3xy. It's equal to 3xy. Now you want to find the relationship between 2xy and x square y square. So you can write it as 2xy plus xy. Now this xy is actually greater than or equal to what? X is less than or equal to 1, y is less than or equal to 1. So x square is less than or equal to x and y square is less than or equal to y. So x square y square is less than or equal to xy. So therefore we get that this is greater than or equal to 2xy plus x square y square. And that's exactly what it needed to show, right? So therefore it's greater than or equal to over here by AMG inequality and the small result where xy less than or equal to 1 we're using. So it's a really beautiful result that we have got, that it's actually greater than or equal to 1 and alpha less than or equal to 1 is actually like alpha less than or equal to 1 is actually a valid assumption. Okay, we have proved that. It's a very beautiful problem. That's why I stumbled over once while doing that. I mean, this is a really beautiful problem. Okay, this will not come in the exams, but it's really beautiful. Like, why? So this family of distributions is a very important family of distribution. Okay, it's like something I forgot the name. It's a very important family of distributions, and it's super important. Okay, let me just see the name. Just give me a minute. The name is Foley-Morgenstern family of distributions. Okay, from two distributions, how we can find a new family of distribution. So, and also this modulus of y less than or equal to 1, this condition is needed. But in this problem, we will show that actually this that alpha greater than or equal to minus 1 is important, but alpha less than or equal to 1 can be actually relaxed. So by drawing in Wolfram alpha and all this stuff, you can actually prove, like, find that the minimum is coming out to be this, which is much more, like it's around 5 root 5. So it's like 5 times, like it's around 10. Okay, so the minimum is around 10 11ish, so which is not really small. And that's why I was facing an issue to show it initially. And you can see the diagram over here between 0 and 1. Here you can see it's a convex function. So actually you can find out, it's a good multivariate calculus exercise. You can actually find out the matrix. Okay, like the differentiable matrix. Okay, and you can actually find out, and you can actually find out and you can check whether it's a convex function or not. It will turn out to be a convex function. Okay, we'll find out to be the matrix to be positive definite, so it will come out to be convex function if you do the double derivative of it. So it's a very important idea, and you can have to show that this function is actually convex, and it's very important between 0 and 1. Of course, between 0 and 1 this function is actually convex, and it's super important. I really like this problem a lot, and because of course I got stuck and I finally solved it. But this is a super important idea, and you can see by contour plot it's taking minimum. In fact, the minimum is being held at the same x comma x point. Okay, so why is that so? Because this is a symmetric function in x and y. This is a high-fi mathematical stuff, so you may need some time to understand that, but this function is symmetric in x and y. So the minimum must be occurring at x comma x. Okay, because if it's occurring at some x comma y, then it must also be occurring at some y comma x, because it's symmetric. Okay, if it's occurring at 0.2 comma 0.5, it also must be occurring at 0.5 comma 0.2. But we know it has a unique minima. Okay, given that it has a unique minima, therefore it must be satisfying at, like, it must be having a minima at x comma x, and it turns out to be this x squared and 1 minus x whole square. In fact, you can differentiate it to find out the minimum over here. Okay, very easily. Okay, it's a really super important, super beautiful. All the ideas are so mathematically beautiful, and it's really like a beautiful problem. And I mean, that is actually true given the Foley-Morgenstern family. It's they're mathematicians and statisticians after all, so they have something interesting going on in their mind. So yeah, so it's a really beautiful problem. I loved enjoying this. I hope you enjoy the solution, and please pardon my like stuttering and like I fumbled over the initial part because I did a mistake in my calculation in the copy. So I hope this like clarifies your doubt why mod of alpha is less than or equal to 1. Okay, so all the best, guys, and stay tuned and stay blessed, and do check out the crash courses we are offering in Cheenta. And also, yeah, and have a very good night, and yep, see you tomorrow. Stay tuned and stay blessed. If you like this video, do like, share, and subscribe with your friends, guys. So bye bye, and have a great night ahead. Bye bye.